Hello students, in today's lecture we are going to learn about electric charges and fields, and this is theory part 4. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So, our topic is dipole in a uniform external field. So here question arises, what is dipole? A dipole is a system of two charges which is equal and opposite. Look at here. Two charges, first is plus q, second is minus q. The magnitude of these two charges are same but sign is opposite. And they are separated by a small distance 2a. So look at here, the center that is situated between these two charges are this one. The point shows the center of the electric dipole. Now, when the dipole is placed in a uniform magnetic field, in that case, the charges minus q and plus q feel a force. But the direction of force of the both charges are opposite. So, this is the system dipole in a uniform electric field. A permanent dipole of moment P. P is the dipole moment. The relation of the P and Q is P equal to Q into 2A. So this is the formula to calculate the dipole moment. So P is in uniform external field E, experiences zero net force but undergoes torque. It means what? It means when a electric dipole placed in a uniform electric field, it feel a force in opposite direction. The direction of the force is opposite. But the net force which is acting on the dipole is zero. But there is a force and that is torque. So the force QE acts on charge positive Q and force minus QE, that is act on charge minus Q. And the direction of force which is acting on charge Q is opposite to direction of force which is acting on charge minus Q. Since the another point here is this, if the direction of electric field is like in this direction, upward, in that case the direction of the force which is acted on the charge Q is along direction of electric field. This is, and the direction of the force which is acting on the charge minus Q is anti-parallel of the direction of electric field. Clear? And from this figure it is clear, that is, look at here, the direction of field and direction of force on charge positive Q both are parallel. Yes or no? And direction direction of force which is acting on charge minus q are anti-parallel to each other. Clear? Since these forces act at different points, first is acting on charge minus q, second one is acting plus q. Therefore, these forces at different points, they create a torque. So, due to this phenomena, they create a torque. This torque's magnitude equals each force's magnitude multiplied by the couples of R. So, look at here. So, the torque is, the magnitude of the torque is QE into 2A sine theta. QE into 2A sine theta, where QE is the force which is acted on the charge. So, this is the torque and the magnitude is 2A QE sine theta. Here, this one QE is the force and this one is the distance, or we can say arm of couple. The direction is normal to the paper coming outward. Similarly, P cross E. So, has magnitude PE sine theta with same direction. So, the vector form of the torque that is represented by tau is this one. Tau equal to P into P cross E. So, we know the value of E is what? We learned it in the topic of electric field, and P is the dipole moment, which is Q 2A. This torque aligns the dipole with field E, becoming 0 when aligned. So here important point is the torque is tau equal to P cross E, where P is the dipole moment or E is the torque. E is the electric field. Dipole in a uniform external field. In non-uniform fields, if we talk about the non-uniform fields, both net force and net torque exist when P is parallel to or anti-parallel to E. There is a same condition, but the field is non-uniform. Torque vanishes, but net force remains. Parallel alignment results in force toward increasing field, while anti-parallel alignment creates force toward decreasing field. This explains why a charged comb attracts paper piece. The comb's charge polarizes the paper, inducing a dipole moment along the field direction. So, the non-uniform field then creates a net force pulling the paper toward the comb. So, this is the phenomena due to which a charged body attract light body. Next is continuous charge distribution. Here we will learn three types of charge distribution: linear charge distribution, surface charge distribution, and volume charge distribution. So, we know charges, the energy of charges having lies in discrete form. So, in our previous discussions, we dealt with discrete charges, and that is Q1, Q2, Q3, Q4 and Qn. While discrete charges offer simpler mathematical treatment without calculus. Many practical situations require working with continuous charge distributions. So here we will learn three type of charge distribution. Clear? So when dealing with conductors, so here question arises, what is conductors? Conductors is a material that allow to pass electricity through them. So here we consider an area element delta S. Delta S, look at figure. Here charges are spread out along the area delta S. Now that's macroscopically small but contains numerous electrons. If we talk about the area delta S, this is a macroscopically very small, but even it contains numerous electrons. And the charge delta Q on this element delta S helps define the surface charge density that is represented by sigma. Clear? So delta S is a small area element and the charges are spread along this area element. Small delta S. Now how much is the charge in this region, delta S region? So to calculate the charge, delta Q is the charge. So in this region, in delta S region, the total charge is sigma into delta S. Sigma into delta S, where sigma is what? Sigma is surface charge density. So it will be sigma equal to delta S divided by delta Q divided by delta S. And this relation is important when we will solve questions that is related to surface charge density. So you remember this, sigma is equal to delta Q divided by delta S. This continuous function sigma represents macroscopic surface charge density. Averaging microscopic charge density over delta S measured in coulomb per meter square. So coulomb per meter square, how we can calculate it? So there is a charge and we know what is the unit of charge, that is coulomb. Yes or no? And delta S is the area element. What is the SI unit of area element? That is meter square. So in numerator, that is coulomb, and in denominator, that is meter square. So it will be coulomb per meter square. It means the SI unit of surface charge density is coulomb per meter square. And the total charge is sigma times of delta S. Clear? And this is the element. We already know this. Second distribution is line charge distribution, or we can say linear charge distribution, when charges are spread out linearly. Look at here. We have a wire, or we can say we have a wire that having length L, and the charges are spread about the small length element delta L. So how much number of charges contains by delta L? So if we talk about the linear charge density, the total charge is lambda into delta L. Lambda into delta L. And another, or we can say third distribution is volume charge distribution. Now, if we talk about the volume charge distribution, the charges are spread out along the volume of this area, this volume delta V. So this is a small element. Initially we consider, or initially we find out the charges due to small volume element, area element, and linear line element. So how much the charge contains by the volume element delta V. So that is delta Q is equal to rho times delta V. And if we talk about the linear charge, that is lambda times delta L. I repeat, this is very important for the exam. Now, for line charge distribution, look at here. This is the representation of line charge distribution. The linear charge density lambda is what? Lambda is linear charge density of a wire, is defined as this one. Lambda is equal to delta Q divided by delta L. And here question arises, what will be the SI unit of linear charge density? So we know delta Q is what? Delta Q is charge that contains by the small element delta L. Clear? And delta L is the small length element. Now what will be the SI unit? We know charge measured in coulomb and length measured in meter. So the SI unit of linear charge density is coulomb per meter, where delta S is a macroscopically small line element and containing many microscopic charge constituents measured in coulomb per meter. Yes or no? I hope this is clear. So similarly, volume charge density rho. So volume charge density is represented by term rho and defined as delta Q divided by delta V. So this is the representation of volume charge distribution, where delta Q is the charge in volume element and delta V is the volume element where charges are spread in this region. Yes or no? Like a cone. Suppose if we consider cone, so like this. So the charges are spread along this, along this. So this is a volume charge distribution. I hope this is clear. Small volume element. And what will be the SI unit? So we know delta Q charge measured in coulomb. So the unit is C, and delta V is the volume. The unit is meter cube. So the SI unit is coulomb per meter cube. So there is a three type of distribution: linear charge distribution, surface charge distribution, and volume charge distribution. This continuous charge distribution concept parallels continuous mass distribution in mechanics, where we consider macroscopic density while ignoring molecular constitution. For calculating field due to continuous charge distribution, we choose an origin O and consider position vector R of any point in the distribution. So the charge density rho varies with position. And the electric field at point P due to charge rho into delta V follows Coulomb's law. We know what is Coulomb's law. So Coulomb's law is uh, it describes the force between two charge particle, and the mathematical term of the Coulomb's law is F is equal to K Q1 Q2 divided by R square, where R square is the distance. So the electric field at point P due to charge rho delta V. Now here is important point. Here we learned linear charge distribution, surface charge distribution, and volume charge distribution. Now using the concept of these type of charge distributions, we will find out the electric field at a particular point using the coordinates of position of the charges. Now here the electric field at point P due to charge rho delta V is this one, 1 upon 4 pi epsilon naught, and the charge is what? Charge is rho into delta V, and r prime square r prime cap. So here r prime square is shows the position. The total electric field by superposition principle becomes this one, and this is important. E is equal to approximately 1 upon 4 pi epsilon naught summation all volume, all delta V. So it will be rho delta V divided by r prime square r prime cap, where r cap prime shows the direction. What is it? Shows direction, where rho r cap and r cap prime rho r prime r cap prime may vary point to point, while mathematically delta V should approach 0, making sum an integral. We maintain this simpler representation. Thank you for your attention.